guys have 12 days to work on that, and it'll be based off the stuff we're doing here. So I'm planning to cover pushover analysis. It'll probably take us another 2 lectures to get through all this stuff. And then we'll move on to covering p-delta effects. And then we'll probably factor the SAP stuff and doing the sort of modeling in SAP with the time we have left. But I wanted to make sure we cover kind of the core stuff so that you at least have that under your belt. So I want to pick up where we left off. We just got to start moment curve or moment distribution for the dead load of our structure. So the way you set up moment distribution is I just basically took this frame and pulled off the column so that everything's vertical now, or everything's horizontal. And then I write the distribution factors above each of those members. So we said for the left-hand side of this frame, 40% of that moment will go into the column and 60% will go into the beam. And on the other one, we have 0.57 will go into the beam and 0.43 will go into the column. And so this initial assumption was that we had the joints between the beam and the column fixed. So we call these the fixed end moments. But the reality is that joint has some flexibility. And so we want to allow that joint to flex. So we're going to release these moments, and we're going to use the equilibrium method essentially. And we're going to add to each of these joints an equal and opposite moment, make sure it's in equilibrium, but multiplying that by the distribution factors. So if we do that, this first iteration, and there's different ways to do moment distribution. There's a technique where you release joints individually. So you go this joint, then this joint, then this joint, then this joint. I'm doing what's called simultaneous moment distribution, where I'm releasing all the joints together. So we release this joint simultaneously, and we'll distribute back and forth from that. So I like drawing a line under each of these numbers when we know we have equilibrium. So the sum of forces, let's say above that line, if we look at this joint, is going to be equal to 0. This is what we expect. But for a fixed connection, if you recall from structural analysis, you will have 1/2 of this moment go to the other end. But for a pin, no moment gets transferred over there. That pin has no moment capacity. So we distribute nothing from here to here. And then what we do is, for a fixed connection, we just said 1/2 goes to the other end. The same applies here. So this is an iterative method. And 1/2 of these forces will go to the other side of the beam, which will give us following numbers. And then we just repeat the process over again. We can see I'm still out of balance now. Instead of being out of balance 10,417 kip feet, I'm now out of balance 3,000. So I just keep going iteratively, and you can see that the more you redistribute, the smaller and smaller your out of balance gets. And so you go to whatever tolerance you're interested in. Usually you go within, let's say, 1% of the initial moment. But you can keep going as long as you like. I did several more. I went down till I was within plus or minus 1 get foot. But to save space and time, let's write what the final moments are. So to get the final moments then, you just sum all the moments on one side of the joint, and we should get the same moment on both sides, equal and opposite. So if you keep going all the way down and you sum all these moments, you will get moment here, that value, you will get that redistribution of moments. So you can draw these on the frame now.
Hey Tim.
Yes.
You probably said it. I just I didn't hear you when I was writing. So you start your first stat your moments are equal and opposite. 1,047.
Those are
Or not,
not necessarily equal to opposite. Those are the fixed end moments we got from assuming the joints were fixed.
Yes.
If you recall from what we did last time, we looked at that dead load and we said the fixed end moments, if the ends of the beam were perfectly fixed, would be WL squared over 12. And we determined what those were then from that equation.
So you lock those from rotating, and then
Right.
you get that, and then you unlock them and you do this.
Right, and that was assuming that the ends of those, or at the ends of the beams and the beam to column joint is completely fixed. There is no rotation allowed there whatsoever. But the reality is that has actual rotational capacity. And so we said, well, we want to distribute that moment then, instead of considering it fixed, we look at the rotational stiffnesses of each of those members, and we distribute that moment based on the proportionality of the rotational stiffnesses of the members. And so that's where I came up with these distribution factors. I was looking at the rotational stiffness of each of them,
Okay.
as we did in the table last time.
Yeah.
And then we took this fixed end moment and said, now, instead of assuming this is perfectly fixed, we have to release this so we get equilibrium on both sides of the joint.
Yep.
That way we don't have, let's say, 10,417 git feet on one side of the joint and then 0 on the other. It doesn't make sense. If you take a cut of that joint should be in equilibrium. So we're then saying, okay, let's unlock that joint and then let's distribute this moment based on these distribution factors, equal and opposite to both sides.
So I get that. You go to the next step. The arrows are you're distributing half to each of the your next joint basically. So you,
Right, because we unlock these both independently,
yes.
and the reality is, as you unlock those, half of this moment will transfer over to the other side. So even though you did this balancing for this one step, after you've done that step, half of that moment will be transferred to the other side, but this is now out of balance as well.
Yeah.
So you want to minimize that out of balance by iterating again.
Okay. So when you get to that next one, you just point right there. They're again equal and opposite. I'm not understanding how you got from where you distributed half to each end, and then you all of a sudden now you're getting what's that? 1,786. I don't know how you.
I took this moment,
Okay.
equal and opposite, multiplied by the distribution factor. Same as I did up here. No different.
Where did you get the 1,786 from?
3125 times 0.571.
Oh. It just ends up being that it's equal for.
Yes,
Oh. Okay.
this is coincidental.
Okay. I'm going. I don't know how you're making that happen.
Yes, I wish I knew how to make that happen.
Okay.
No, that's coincidental that these are equal.
Okay.
You can see sometimes they're equal and then sometimes they are not. It's just
Okay.
coincidental based off what these factors are and all those different things. But yes, you just look at this one joint, you distribute this joint equal and opposite to make the sum of these forces 0 by multiplying this distribution factor times that and flipping the sign. And then you keep going again. Once you have this, half of this goes over here, half of this goes over here, and now this is your out of balance in that joint. Yes?
They're actually not coincidental. They are, every other iteration, they are equal because they get cycled. They start with the same number, but they get cycled through the same multipliers every second iteration.
If you're only considering flexure, yes.
Right.
If you consider shear and moment distribution as well, that changes.
In this model.
In this case, yes. So the point of this now is we can get, once we know these end moments, we can get the shears associated with these moments. So we have a shear force, let's say at joint A, and a shear force at joint D. These are, let's say, the base of our frame. And then we'll get an equal and opposite up at the tops of each of these. And we can solve for these forces just using statics. So if we look at this member right here, And you can take moments about either point. Took moments about B. I found that the reaction at A, their VA, is 293 kips. So you take moments about B, you have VA is rotating this direction times that 30 feet, and then your 2929 and your 5860 are rotating the opposite directions, so your sum of your moments is equal to 0, and you will get that. We can also do the same for joint D. We find that VD is 212 kips. And so what you may recognize now is that VA and VD should be equal and opposite if this frame is in equilibrium. But these forces are not. And what this means is our frame has sway. So this was taking no sway into account for our analysis. We need to balance out the sway of this frame. And to do that, we look at, okay, these forces should be equal and opposite, but they're not, which means we have to have, let's say, another reaction up here at the top of the frame. In this case, it would be going like so. We'll call this RB. So then we'll say the sum of forces in the x for the frame is equal to 0. So we have VA minus RB minus VD. So we find that out of balance lateral force is 81.3 kips. And what this means is the frame will now sway before it achieves equilibrium. And it'll sway to a certain point such that this 81.3 kips will disappear. So the way we want to solve for is I'm going to look at what happens if we take this frame and we apply just an arbitrary lateral load to the top. And the reason we're just going to apply an arbitrary load is we'll scale it to whatever we need it to be, based off of that 81.3 kips later. But for now, we'll just start with the unit. Let's just say 100 kip load. Up here. We're now looking at the translational behavior of this frame. So we want to look at the translational stiffness of each of these members. So we have a fixed member on this side. We have a fixed pin member on this side. So if we look at member AB, for a fixed, translational stiffness is 12 EI over L cubed. And if we look at member CD, this is a fixed pin, so the translational stiffness here is 3 EI over L cubed. And the sum of these would be 13.2 EI. The same idea, we want to look at the ratio of member AB to the total translational stiffness of the frame. So the total translational stiffness would be the sum of these two members. But how much stiffness the first one has relative to the total? About 72% versus 27%. And of course, those sum to 1. So what this means is we're going to develop a reaction at the base of the frame to this 100 kip load based on the distribution of those translational stiffnesses. So if we have a 100 kip unit load, this is why it's handy to do it this way. You just take 100, you multiply by this distribution factor, and you get 72.7 kips there. You get 27.3 kips here. What happens now, look at the deformed shape of this frame. Each of these columns is going to deform like this. And what you'll note is that the fixed column has an inflection point in the middle. So that's BA. You'll get an inflection point where your shear switches directions, the center. And for the fixed pin column, you won't have that behavior. So what you can do then is you can develop moments at the fixed ends of these columns based on these shear forces. So this is accounting for this sway of the frame. And so the moment for this guy right here Those each could be 15 feet. So we'll have, let's say, moment at A, moment A, moment D. So there's no moment down there. Moment D up here. Moment C, it's a joint C. So if we're getting the moment at A, this is just the shear force VA times that distance to the inflection point, which is, in this case, 15 feet, or L over 2. And for this one, we just have the shear force VD times that length L. And we end up with 818 kip feet. So now we just do moment distribution again, but we look at, instead of having the fixed end moments in the beam from the distributed load that we started with, we now look at the fixed end moments in the columns based on this lateral force behavior of the frame. And then what will happen is we'll take these results and we'll scale them so that we allow the frame to sway by balancing this result with what we had before. So these are our fixed end moments to start out for this translational force.
Shouldn't we be using the R's that we came up with? Translation?
No, this is a rotational analysis still. The translational stiffnesses were just for distributing this lateral load to the base of the members. But now we're doing the same sort of analysis where we said these moments develop at the top of the column here and the top of the bottom here. And because they've developed and we said everything is fixed, it's not actually fixed. We need to let this frame rotate. So that's why we're using the same distribution factors here. And we'll just do the same process now. Once again, is doing simultaneous release of the joints. I look at this out of balance moment at the joint, I multiply it by an equal and opposite moment. This is distributed by the distribution factors. So 40% of this will go to this side, 60% to this side. For this joint, 57% will go to this side, 43% will go to this side. And as we do this, we end up with half of these transferring over as before. And then we distribute again. Once again, I want a few more cycles, but I'll abridge that here. Just to get clarity. So we end up with those as our final moments. And so even though we said we were applying a 100 kip unit load to start, the reality is when we let this frame flex and we don't completely fix things rigidly, like we assumed with these translational stiffnesses, we're going to have a reduced amount of lateral force applied. And so we can find out how much that actually is by looking at these moments we had and then going back and solving once again for VA and VD. This is once again based off the free body diagrams. Just as before, we looked at, let's say, the free body diagram of just joint, or member AB and member Civ E. I'm just abridging it here for space. So the goal here is we found out now what is the actual lateral force we're applying so that this frame will translate to the right, develop these end moments, and we ultimately get 73.6 kips will result in these end moments. So what we have to do then is we want to take this force VB now and scale that to be equal to the 81.3 kips we had out of balance. We said the frame had no sway, or we assumed it had no sway. So for here. I'm interested in the scale factor for that. Where I wanted to scale based off the shear force we found that had to be reacting at the top of that frame when we didn't allow sway versus the shear force we're getting now where we're allowing translation. And then we just want to add these systems together. So we'll scale the system over here now, all those moments, by the scale factor of 1.104. Because what that will do is that will make all these moments develop a shear force at VA of BD that would be equal to a VB of 81.3 kips. And then by adding these results together, now we take out that sway from our original frame, and we now have equilibrium once more. So you can visualize that like this. So I just take these two systems now, and I add the moments at each of the joints together. solve for VA and VD, you will find that they're actually equal and opposite this time, which is what we wanted. And this tells us our frame is now in equilibrium. So we've allowed this frame to sway, and we now have the final end moments that are associated with that dead load, with both the load applied and the frame's sway. So this is important to us because we want to know, by doing all this basic analysis, how much moment capacity has been used in each of these hinges just from these dead loads. And now you can tell how much moment just from the dead load of your frame is present by looking at these moments. And so our analysis is we're just going to keep pushing this over to the right. This is what we call pushover analysis or an event scaling analysis. And we're going to keep pushing over then until this lateral force keeps increasing these moments such that one of these joints will develop the plastic moment in it. And once that occurs, this behavior will change from behaving like a fixed connection to behaving like a pin connection. And so the idea is we keep pushing this over, we keep letting joints form hinges until we get a mechanism in the system where we can no longer transfer forces. So that increased lateral load, you have no force transfer, your frame just falls over and fails.